let's continue with our discussion on fields, electromagnetic fields and waves. So last day we were discussing about some differential operators which we use on vectors. So today another topic which we need for our discussion of electromagnetic fields is Fourier transforms. So okay, so we will start with our discussion on Fourier transforms. Fourier transforms. So now, first let me define what a Fourier transform is. Okay, suppose we have a function. Suppose we have a function f of t. So this is a function in time. Okay, now the Fourier transform of f of t is defined as the Fourier transform of f of t is defined as transform of f of t is defined as, we can write f of t as, we will write in notations. Okay, f within square bracket f of t, okay, is actually equal to integral negative infinity to infinity f of t e raised to I omega t dt. Now let me
Is there 1 over square root of 2 pi?
yeah, I will tell you that. So 1 over there are certain things. So 1 over square root of 2 pi is there. So different textbooks use different notations. Some textbooks use 1 over square root of 2 pi, and some even say that some even take the Fourier transform as e raised to negative I omega t instead of positive I omega t. It depends upon, so just like that there are just like how we define a origin.
So
there are
that 1
different
over square root of 2 pi is taken as 1, right?
Yeah, taken as 1. No, yeah, it's actually 1 over 2 pi is used to normalize the Fourier transform, but we are not going into that. Okay. Now, so when we define this Fourier transform, we will always get a function f of omega. A function this omega. Okay. Now, once we define Fourier transform, we have to find, we can also define what we call inverse Fourier transform. Inverse Fourier transform is written as f inverse is equal to f of t is equal to negative infinity to infinity f of omega, because we are taking f of omega as we are taking the inverse of this Fourier transform of.
So in the left hand side
also there should be omega, f of omega. Okay, it will be equal to e raised to negative I omega t or d omega equal to f of t. So actually this is the equation for Fourier transforms, and let me just make it a little big. Okay, this is the equation for Fourier transform, and this is the equation for inverse Fourier transform. Inverse Fourier transform. Now, why do we use these Fourier transforms? That's, yeah, so it's a general way to define Fourier transforms when we are dealing with ordinary differential equations. Suppose, the idea is this. Suppose you have a very difficult problem. Okay, you cannot solve those problems directly in normal space. Normal space in the sense, if you are using normal coordinates and other things, we cannot solve this. that problem, that physical problem. Then what we do here is we'll transform it into a much simpler space. Okay, so this Fourier transform, and there is another type of transforms called Laplace transforms. They are usually used to take these complex problems and transform into another plane or another space where the problems are much simpler. Okay, then if you we will find the solution there and take the inverse of the solution. Then we will get the solution in our actual space. That's the idea there. So it will become much more apparent when we actually deal with when I actually define certain properties of the Fourier transforms and certain properties of Fourier transform and how we apply those especially when we are applying it on what we call as Maxwell's equations. So let's start by looking at certain properties. Okay, so I will define certain essential properties. We will look at properties here, properties of Fourier transform. So Fourier transforms are essentially what we call as integral transforms. And since they are almost an integral, the property like linearity of the integral applies here. What do I mean by that? Let's discuss. So suppose you have a combination of functions. For example, let's say a. So first we are discussing linearity. Suppose you have a combination of functions. Let's say a f of t plus b g of t. Okay. Suppose you have a combination of this function. Then if you take Fourier transform of f of omega will simply be equal to negative infinity to infinity f of t e raised to I omega t dt. And g of omega, the Fourier transform of omega g will be negative infinity to infinity g of t e raised to I omega t dt, isn't it? Now let's find out what will be the Fourier transform of this function, this combination as a whole. Okay, so Fourier transform of a f of t plus b g of t, that would simply be equal to it will be equal to a times. No, it's not like that. It will be equal to integral negative infinity to infinity a into f of t plus b into g of t, the whole multiplied by e raised to I omega t dt. Now we can simplify this, isn't it? These are certain simple algebras here. Now we can just simplify this as it will be equal to negative infinity to infinity a into f of t into e raised to I omega t dt.
Joe, the line before that you wrote minus I omega t.
Yeah. That's okay. I omega t. Okay. T dt plus integral negative infinity to infinity b into g of t e raised to I omega t dt. That is simply equal to a into integral integral f of t e raised to I omega t dt plus b into integral g of t e raised to I omega t dt, isn't it? Now this is simply equal to, I can write it as a into Fourier transform of f of t plus b into Fourier transform of g of t. This is what we call the linear property of Fourier transforms. Okay, so as I said before, we can transform Fourier transform. We can see that the linearity of the integration or integral applies here also. Okay, now let's come to the most important or one of the most important properties of Fourier transform, that is the transform of derivative. Okay, transform of a derivative. Here is where our here is where our idea of this Fourier transform help us. Okay, here is where the idea of Fourier transform help us. Suppose, so we know how to Fourier transform a function, isn't it? Now we are going to take, suppose you have a, suppose f of t is a function. Okay, and d by dt of f of t is continuous. And also, whenever we take a Fourier transform, we assume one important thing. That is, let me draw. One important assumption here is f of t is equal to 0 at negative infinity and positive infinity. Okay. This is an assumption. Okay.
F of t equals 0 at
Negative infinity. Negative and positive infinity, because it means that the function doesn't blow up.
Okay.
Okay, function is a converging, we can say it's a converging function. Otherwise, it shouldn't blow.
It has no effect at
negative
as
and positive.
We move farther away.
Further away, yeah. Now, so as we are discussing this, let's find the Fourier transform of this derivative. Okay, so f of d by dt of 50. Okay, now let's simply apply our rule of how to find the derivative. Okay, so this will be equal to integral negative infinity to infinity d by dt of f of t into e raised to I omega t dt. Any ideas on how to solve this?
They like product rule use.
Yeah, we use integration by parts. Okay, so what is the equation for integration by parts?
First suppose
yeah, it's like this. We suppose you have u dv. dv is equal to u into v minus integral v into d. Something like that. Okay. Or first into integral of second minus integral of second into derivative of first. This is the this was the equation. Do you remember? It's a 12th.
Yeah, I just memorized like the first in the integral of second minus integral.
Okay, let's okay. Let's do that. Suppose you have two functions. Okay, let's do like that then. Okay, so it is like, so what is the first? What should be the first one? First function. First function. We have to select this. Which one is the first?
Yeah.
I'll take this as my first.
Okay.
E raised to I omega
so
t.
The derivative will be that itself.
Yeah, I'll take this as my first function. Okay.
The derivative and the integral are the same.
Yeah. First, and this as my one. Okay. Hello, can you hear me?
Okay.
Yeah.
Are you sure?
Okay.
Let's do it anyway.
Yeah, let's do it. Okay. I'll take this as the first one and this as second one. Okay. Okay. Yeah. So it will be equal to what will be the value?
First function into
first f of t into.
No. first function means e raised to
e
I
raised
omega.
to omega t, e raised to I omega t into
The integral of
f of,
second function. So
yeah,
f of t.
it will be f of t, isn't it?
Right.
Within the limit negative to positive infinity. Okay.
Minus
integral of
derivative of first into
derivative first, that is I omega e raised to I omega t into
integral f of t.
F of t, isn't it?
Yes.
Now
put the limit.
Okay. Now let's. Okay. So this was the. Now let's rewrite this e raised to I omega t f of t from negative infinity to infinity. Now this I omega is a constant. I can take it outside. Okay. Infinity to infinity. Let me write. There's a dt here. Okay. F of t e raised to I omega t dt. Okay. As I said earlier, at negative and positive infinity, f of t becomes 0. So, okay, so this whole thing will amount to 0. Okay. Now, what is remaining? Negative I omega into infinity to infinity f of t e raised to I omega t dt. That will become negative I omega into, what is the value?
This is the Fourier. This looks like Fourier transform.
Yeah, f of
t. Oh, okay.
So taking a time derivative actually adds a constant to the derivative. Now, if you take a derivative second time, what will happen? If you take a second derivative, what will
happen? Minus I omega.
Yeah, will be added. Okay, you can. Okay, you can like as a homework find.
Yo, just don't give me homework. Even though I'm lazy. Let's do it.
Yeah. No, you don't have to do it. It's.
Please, I'm begging.
Okay. Okay, let's do the second derivative also. Okay. So it will be. It's actually very simple. You can do you can do this. Find that without using this integral or anything like that. I can write it as. Okay. Let's talk about second derivative. Okay.
Joe, before that, just write that formula. F of d.
Yeah, I will write it. Okay. So that will be equal to. So what we have found here is that Fourier transform of d by dt of f of t is actually equal to negative I omega into Fourier transform of f of t. Isn't it? So this is our equation. Okay. Now let's move on and find the next important point. So Fourier transform of second derivative. Okay, Fourier transform of second derivative. Okay, I can actually find this by using this first derivative. Let's look at it. Okay, f of d by dt or d square by dt square of f of t. That is what we are going to find, isn't it? This is simply equal to f of d by dt of what?
D by dt. Okay.
D by dt of f of t, isn't it? Okay, that is actually equal to
minus.
One second, d by dt of f of t. That is negative I omega into f of. That is I am taking this first. Okay, that will turn to this I omega here. Okay, f of d by dt of f of t. Okay, then again taking, it will become
again negative I omega times negative I omega.
That is negative I omega square, isn't it? Or I omega into f of t. Or simply, I can write it as negative I omega square f of t. Okay.
Okay. So we can find the general.
Yes, generally we can say that. Generally, I can write generally Fourier transform of d by dt nth derivative of f of t with respect to time. Okay, with respect to time, not with respect to any other quantities. Okay, will be
time meaning the variable in which we are taking
variable. Variable in which we are taking the Fourier transform. Okay, f of t.
Since we are studying physics, we are usually taking time derivative, right?
Yeah. Because dynamic, whenever we are talking about dynamics, we are talking about dynamical properties or waves or anything like that. We are interested in how the wave changes with respect to time and position, isn't it? Space. So actually, when you look into these kind of things, you should the Fourier transform in time space or Fourier transform of time usually leads to a function in frequency.
Frequency, yeah.
Isn't it? Fourier transform in time leads to function in frequency, isn't it? Function in frequency domain. Frequency domain. And Fourier transform in space. What will it lead to?
Spatial frequency. 1 over.
Think about Brillouin zones.
Wave vector.
Wave vector function in actually wave vector space, or it is actually momentum space when you talk about it.
Okay.
Okay. So actually we are here, we are only concerned about Fourier transform in time. Okay. Now here is the idea. Okay. Suppose you have an ordinary differential equation. Okay. Suppose you have an ODE or a okay. Suppose you have an ordinary differential equation like this: dy of dt is equal to some let's say f of t. Okay. Now the idea of Fourier transform is actually if I take the Fourier transform of this whole equation. Okay, I am taking the Fourier transform of all equation that will be equal to negative I omega y of omega is equal to f of omega. So what happened here?
The derivative is gone.
Derivative is gone. This ordinary differential equation changed into an algebraic equation, which is easier to
linear equation. Okay.
Yeah, which is easier to solve.
Okay.
Which is easiest to solve.
Yes.
Algebraic equations are easier to solve than for ordinary differential equations, isn't it? So actually, what happens is that Fourier transform of an ODE, ordinary differential equation, will give you an algebraic equation. Okay, so from this equation, it is actually from, for example, as we said, from this equation, if we do this y of omega, what will be? F of omega divided by I omega. Okay, all you need to do is take the inverse Fourier transform of this. Okay, which can be easily done. Compared to solving the whole differential equation.
But this equation is easier to solve by
This
integrating.
equation, yeah, this equation is very easy to solve by integrating. But you got the idea, right? Isn't it? So now let's talk about let's talk about it in much more not in much more detail, but you got. I hope you got an idea, isn't it? Now, what happens if I have a partial differential equation? What will be the use here when we have a partial differential equation? What will happen if I take the Fourier transform of partial differential equation? Could you just guess?
Meaning we can only take with respect to one variable. Is that what?
Yeah. When we take the partial derivative of, usually when we take the Fourier transform of partial differential equation, it will turn into an ordinary differential equation. Okay.
Okay, so, but that needs a demonstration, I think.
Yeah, I will show you using. Okay, so I think it's high time that we delve into a little bit of our, what we can say, delve into what we can say as our Maxwell's equations. Okay, so let's talk. Let's talk about using these Fourier transforms. Using Fourier transforms in Maxwell's equation. Okay. So when we use this Fourier transforms in Maxwell's equations, we can actually what we get here is an idea of how this. There are two things. We will learn about Maxwell's equation as a whole, and the second thing is that we will learn about how this Fourier transform help us in solving Maxwell's equation. Okay. So, okay, now let's start. Okay, so I am going to introduce certain small notations. Okay. Okay, so it's for the ease of writing. Okay, notations. Okay, so I can write dou by dou. I will write it as dou by dou s as simply partial derivative. Okay, in the same way, partial derivative with respect to time, I will just write it as dt.
This is pretty standard notation.
Yeah,
these are
standard notations, but sometimes people get confused with these as well. Okay, so let's start. So what are the Maxwell's equations? Let's start from Maxwell's equation.
Del dot.
Let's start from the Gauss's laws. Okay, Gauss laws. Okay.
Del dot E equals rho.
Del dot E is equal to rho over epsilon 0. Okay, if I take partial, then we have del dot B is equal to 0. So these are the Gauss's law. Gauss laws. Now now we have what do you need?
Curl equations, right?
Curl equations. What are the curl equations?
Del cross
E equals, del cross E, or here we can call this some textbooks call it as curl E also, equal to negative
dou B by dou T.
Yeah, I'll write it as this. Okay. Similarly, del cross B or curl B. What is this? What are this equation?
This is Ampere Maxwell, right?
Yeah, epsilon 0, mu 0. dot E plus mu0 times.
Yeah, right. Okay, but I remember del cross H, because when you divide by mu0,
these are So actually, there is a specific name given to this. We will give a specific name. These are microscopic Maxwell's law, Maxwell equation, because these usually give them. These are actually without what we can say. These laws actually are not including the material properties. These are all in what the only thing here we are adding. We are taking this in free space, isn't it? So, okay, microscopic Maxwell's law, or we can say Maxwell's law. It's better to name. Better word is here. A better word to note here is Maxwell's equations in free space.
Right.
Equation in free space. Okay. Now, if you take,
because in the presence of a charge, these equations.
Not in the presence of a charge, in the presence of charges, or in the presence of a material medium like a dielectric or a metal, the whole thing changes. We'll discuss that also.
Become non-linear, right?
Yeah, it's become non-linear. Now let's talk about these two equations. Okay, these two equations, if you take a Fourier transform of these two equations, it is not going to give us any extra. It is not going to solve anything, or it is not going to give us any extra informations regarding this, because these are all differentials in space or spaces. There is no time derivative here. But let's talk about these two. Okay, if you take a Fourier transform of these two equations, it will
can we take Fourier transformations? Is there a problem in taking?
No, it won't be there won't be any problem. But okay, let's check. Let's check one by one. Okay, I will do one of Gauss's law. Okay, I will do this first one. Okay, this one and show it. Okay. So it's not
because
like,
that would be an easier place to start.
Yeah. So let's talk about the Fourier transform of this equation. Del dot E of this electric field is electric field of position time, isn't it? Is equal to Fourier transform of rho of position time epsilon 0.
Joe, you should have also mentioned what is a Fourier transform of a constant.
Fourier transform of a constant. We don't take Fourier transform of constant. It will be a constant itself, isn't it? I told we discussed that indirectly when we are discussing the linearity property. The A comes outside, isn't it?
No, but that's a constant times a function. But what will, because this is a constant in the right. It will be, I think.
No, actually, we are taking most generalized equation here. So we cannot be sure that the charges.
No, this rho is a function of R and T, right?
Yeah.
So then it's not a constant anymore.
Yeah. So it can be actually when we talk about the Fourier transform, Fourier transform, because charges may be produced or destroyed or something like that. We are taking this as a function of
be produced or destroyed.
Produced can be created and annihilated. Casimir effect.
Oh, but that's a quantum effect.
Yeah, that's a quantum effect, but it is if there is a suppose we are taking
change in density with
charge
respective space.
Charge density. For example, suppose
These are dynamic equations, so charge
may change. Or a simple example I can give you. Suppose you have a spherical charge density, equal spherical charge density. Okay. Now I am applying a changing electric field here. Okay. This electric field will in turn changes this charge distribution by force acting on it, isn't it? Okay. So at the actually this is a advanced concept, not advanced. The electric field that suppose we electric field at T will change the charge density at T, isn't it? Charge density at or electric field at T will give a charge density at T plus some dt, isn't it? For later time.
Okay.
You're not getting that idea.
No, just not get into that idea.
Okay, we will discuss that. It's an important concept because causality. When we talk about causality, instant actions cannot happen, isn't it?
Yeah, right.
Okay,
one has to affect another.
Yeah, one has to affect another. Locally, one has to affect another. So what happens here is that the charge density at this instant is due to electric field or magnetic field at an instant before that.
Oh, okay.
That's what I was saying. So electric field actually affects charge density. The shape of charge density can be changed.
Value of charge density.
Yeah, density, value of the charge density. The shape of the distribution may itself change, isn't it?
Okay.
Okay, so that's why I'm taking off R and T.
Joe, you should have explained what these terms are because someone.
No, most of them already know. This is charge density. Okay, let's talk.
Only you don't know.
Yeah, only you don't know. Charge density.
Me.
Yeah. Charge per unit volume. Okay. If I take a Fourier transform of this, it won't give us any particular new information, or it won't simplify this equation to be exact. Because if you take the Fourier transform, this will be simply be del dot E of R. Instead of T, we will get an omega. Okay, this will be R omega epsilon 0. Epsilon 0 actually epsilon 0 omega. Epsilon 0 will also be a function of omega. We'll talk about that. There is a relation.
Epsilon 0 is no. Is it a function? It's a permittivity free space.
Epsilon 0
is a constant.
Talking about epsilon 0. Okay, I'm talking about the macroscopic picture. Okay, so same thing happens if you take the Fourier transform of del dot B also. There is not much information that we can get from this equation. It will not simply saying there is no point in doing the Fourier transformations of Gauss's law because there is nothing. It will not simplify the equation.
Okay. I got it. Because let me discuss. Let me tell my idea. Because the del dot the divergence is when you take divergence, we are taking derivative with respect to x.
Because x, yeah, space.
So in order to solve that equation, you would have to find the Fourier transform in x. But here we are taking t. That leaves with the no effect there.
Yeah, exactly. Now let's talk about these two. Okay. Let's discuss the second curl equations. Okay. So let's talk about it.
But those in the curl equations, there are time derivatives. So Fourier transforms can be applied. Is that the idea?
Yeah. Curl E of R T is equal to negative dou by dou T. Let me write it as okay. Dou by dt is B of R T. I'm going to take the Fourier transform. Okay. What will be the answer? This will be curl of E of R omega will be, what will be the answer?
Minus I omega.
Omega. Okay, my negative of negative I omega B of R omega. That will be equal to I omega B of R omega. Okay. So essentially what happened is that this whole partial derivative essentially changed into an ordinary essentially changed into an algebraic equation. Isn't it?
The derivative has gone.
Derivative has been gone, or it vanished. The derivative vanished in the sense. Okay. You get the idea there? Okay. Same thing can happen when we take the derivative of the second curl equation also. Let me take. Okay. Sorry, Fourier transform of second equation, curl of B is equal to.
You're right, del cross B. That's much more easier to.
Right. Del cross B is equal to epsilon 0 mu 0 dou by dou t of E of RT plus mu 0 J RT. Let's take the Fourier transform here. What will we get?
Okay, the LHS B becomes R and omega. B of R of omega.
R omega.
Del cross.
Del cross B of R omega epsilon 0 mu 0. This will be negative I omega E of R omega, isn't it? Yeah, E of R omega plus what will be the answer? Mu 0 Jm of R omega. Okay, so here actually del cross B is equal of R omega equal to negative I omega.
Jm was a displacement current.
Yeah, displacement current. Yeah, it's displacement current. Yes. Zero. So this is what Fourier transform do. Okay. Now there are certain things. Okay, before we will look at Maxwell's equations. More specifically, the macroscopic Maxwell's equation or material Maxwell equations. More detail. And one thing I want you to understand here is we'll discuss that in the next session. That this here we are only discussing about epsilon 0, the permittivity and permeability of free space. Okay, but when we are talking about material Maxwell's equation, let me just write here. Okay, this let's talk about material Maxwell's equations also. A small introduction. Okay, it's better to discuss that in the next class, but let me just write material Maxwell's equation. Material Maxwell's equation means
Maxwell's equation inside a medium.
Maxwell's equation. Okay, that is Maxwell's equations in a medium. Essentially, Maxwell's equations in a medium. Okay, what are those? We'll discuss. We have to discuss a little bit. So first one, we'll talk. First, we always write with start from the. Let's start from the Gauss's equations. Okay, Gauss's law equations. So it is actually del dot D. What is D?
Displacement.
Displacement.
Sorry. Electric displacement.
Yeah, electric displacement. Okay, divergence of electric displacement is equal to the amount of free charge or source. Okay. So what is electric displacement D actually?
epsilon times
Hmm.
E epsilon 0 E, right? E epsilon 0 something.
Yeah, actually, let's there are several equations. Well, D is equal to, we write it as epsilon 0 E times polarization. Actually, what does this?
Right.
This
For
can
free space, there are no materials, so polarization.
Yeah,
right?
polarization. Yeah, polarization will be
0.
So now, actually, yeah. So what is this D? Electric displacement. What is the physical significance here of D? It is we can simply say that this D is one second. This D is actually the effect of electric field inside a material. Okay, I will discuss that. I just want to give you what we can say as a preview of what to come. Okay, del dot. Now, del dot B or del dot H, both of them are right. We usually write del dot B here. Hello, can you hear me?
I can hear.
Okay, del dot B will be equal to 0. Now is the other equation, del cross E. That is actually equal to negative dou by dou T of B. And this is the equation del cross H. H is, what is H?
H is mu 0. Sorry.
Yeah.
Mu 0 B.
1
over
mu 0 B. H is equal to 1 over mu 0 B. I will write both D and B later. Okay. It will be equal to dou by dou T of D plus J. Okay. Now, this is the Maxwell's equations. Okay. Now, when we talk about these things, actually, there are several equations for D and all things. Let's write it. D can be written as epsilon times E. Here, epsilon here is absolute permeability. Absolute permeability of the medium. Okay. Absolute permeability.
Permitivity.
Permittivity, sorry. Not permeability, permittivity. Okay. Permittivity. It can be written as epsilon 0, epsilon R, where R is the relative permittivity. Okay. Now, permittivity. Okay. Now, next thing that we learn here is H. H will be 1 over mu B. Mu is the absolute permeability. And here is a kicker. When we come to Fourier transforms, when we are dealing with this Fourier transforms and everything, when we come to this Fourier space while dealing with this, we'll find that this absolute permeability, relative permeability and absolute permeability are not constants, but they are a function of omega and are complex. Okay.
So that needs a bit demonstration.
Yeah, that we will do in the next class. A prelude to next class, the next session. Actually, it can be and the concept that we need to understand here is that I talked about it. So when we discussed, we all know about RLC circuit, isn't it? LCR circuit.
Yes.
Okay, in LCR circuits, there is a phase change between voltage and current. There is a phase change, isn't it?
Phase difference.
Phase difference. Yeah, there is a phase difference. Usually, in order to account for this phase difference, we use phasors, or much more in the sense we use complex quantities to explain this phase difference. Okay. Okay. In a similar way, there is a phase difference between this D and E and H and omega and all H and D and all those things. Okay. When actually this comes to the when we are talking about it, this actually is due to
the wave nature.
Wave nature. There is a phase difference. Sometimes there is a phase difference between what electric field and the magnetic field of a wave, isn't it? Okay, so this is actually due to the frequency response, and the complex nature of this can be attributed to the frequency response or frequency dependence, and the complex nature of this permeability and permittivity. Okay. So essentially, what we from now on what we do here is when we are taking the Fourier transforms of all this, let's take it. That will be much better. Okay. That will be much better.
Just don't leave me in suspense.
Yeah. So so here what will be the here there is no point in taking. Okay, let's talk about. Let's do that. Okay, so this will be when we talk the Fourier transform of here, Fourier transform of del, del cross E is equal to negative dou by dou t of B. Let's take Fourier transform. Okay, what will the Fourier transform? It will be equal to.
This is the same as
the earlier one. Yeah, earlier equation, isn't it?
Yes.
Okay. E del cross E of R omega, K of R omega. Actually, this will be equal to negative I omega B of R omega. Now let's take the Fourier transform, the other one, del cross H. Okay. Del cross H is equal to dou by dou t of d of R t plus j of t. Okay, when you take it, what will be the answer? Del cross H negative I omega d of R omega plus j of R omega. Okay, you might think that this is same as before, but there is a crucial difference. Okay, what is H? H is 1 over B.
1 over mu 0.
1 over, yeah, 1 over mu 0. So actually this can be rewritten. Okay, let me write del. Okay, let me down a little bit. This can be written as like this. Del cross 1 of mu of omega. Okay, B of R omega. Okay.
So the absolute permittivity is a function of omega.
Yeah, it's a function of omega. Will be a function of omega.
Is there a term called relative permittivity? No.
Yeah, there is. Yeah, it is because the relative permittivity and relative permeability are the function of omega, functions of omega actually. So this will become I omega. What will be the value? I omega. D can be written as E of omega, permit E of omega into E of R omega plus J of R omega. Now this will become this on rearranging, we will get del cross B of R omega is equal to negative I omega mu of omega E of omega into E of R omega plus J of R omega. Okay. Actually, did you get the idea here? So the This is essentially what I'm saying. This is actually, we'll discuss more about it in the next class. But essentially, what happens here is that this mu and so this absolute values, or whenever we are, whenever we are
medium,
the mediums, the permeability and permittivity are frequency dependent. Okay, whenever we are dealing with mediums, E of permeability and permittivity are frequency dependent. And permittivity are frequency dependent. Okay, what is the consequence of this? We can see the consequence of this in a lot of things. For example, this okay, we may have heard about waveguides, isn't it? Okay, waveguides offer the transmission of waves of a certain frequency only. Coaxial, okay, coaxial cables will only allow certain frequencies to or will allow only a value of certain, or only allow the electromagnetic waves of certain frequency ranges to pass through them. Okay, okay, but optical fibers will, for example, for waveguides, it's I think it's in around certain megahertz or around certain gigahertz. I think that is the maximum range. Okay, I'm not sure. I'll have to look into it. But optical fibers can have up to terahertz of frequencies to pass through them. So it is actually, so this frequency, it is because the mediums of this optical fiber can handle up to certain terahertz range of frequency. They can handle the frequencies in the ranges of terahertz. Okay. Waveguides can handle the frequency in ranges of gigahertz. That's why we use different things for different application. Waveguides are usually made up of metals. Okay, so metals can actually have certain properties like reflection, transmission, and all those things. Okay.
So I think you have to explain this in great
details. Yeah, we will explain this in great details later. But I think you got the idea. Due to the frequency dependent.
I got the idea of where we are going.
Yeah, that's what I want to know. Wanted to impart. So
but let's not go there.
Yeah, so actually you might think like this. Why can we use actually metals have, you might think about like this. Metal has a great confining property for electric fields, isn't it? No electric fields can penetrate a metal, isn't it? A hollow metal.
Yes. Due to Gauss's theorem, Gauss's law. What's that?
Yeah,
it's like a Faraday's cage.
Faraday's
depend on Gauss's law.
Actually, it's not exactly dependent on Gauss's law, but you got the idea, isn't it?
Okay.
So why can we have a metal tube that can transmit all type of frequency? Because metals can only handle certain types of frequencies without attenuation. Okay. This attenuation and all those things depends upon what? This E of omega, epsilon omega and mu of omega. Permeability and permittivity. Okay. So since permeability and permittivity are frequency dependent, they cannot transfer.
That means they are made to handle certain frequencies.
Certain frequency ranges. Yeah, certain frequency ranges. Optical fibers are used to handle certain frequency ranges because they have the mu of omega and or permeability and permittivity suitable for that frequency ranges.
Okay. Okay. So let's. I think let's discuss that
next class.
Okay. Also, before discussing that, you would have to explain how this equation becomes a wave equation.
Yeah, I will discuss that.
Okay, that's because
actually,
when we are going to discuss waveguides,
actually,
we still haven't solved this equation.
No, we still haven't solved this equation. Actually, what we are going to do next class is actually we are going to look into what we call Lorentz model and Drude model. Okay. Lorentz model and Drude model are actually equation or models which tells us what happens when an electric or electromagnetic wave interacts with a dielectric media and a metal. Okay. Lorentz model is for a dielectric media and Drude model is for a metal. Okay, so we'll look at we will look into that. Before looking into that, we have to learn a little bit more about Maxwell's equations. Okay, we'll have to talk about what we call there is a what we call a convolution relation. Okay, we'll discuss that when the time comes. Okay. So let's stop for today and see you all in next class. Okay.